So hopefully we're pretty familiar with two-dimensional things. That's what we've been graphing in for many years in math class. So x and y are the two variables we use most often for two-dimensional representations. And it'll normally look like our regular Cartesian plane, which has our x-axis there horizontally and our y-axis vertically, and our origin is at 0, 0. So how can we represent the solution to x equals 5 graphically? Can I think of more than one way? Now I can recognize that one variable means that there's only really going to be one dimension that I need to represent. And the way that I can represent a single dimension, if we bring back our stuff from chapter 4, is a number line. So this number line just represents my x values. I can start at 0, and then all I need to do is put a single point at 5. Now I could also represent a single variable in 2 dimensions. So I'm going to draw my x and my y axes. And then in the place where I have x equaling 5, in one dimension I have a point, but in 2 dimensions it is that entire line wherever x is going to equal 5. Part B, representing our solutions to x plus 2y equals 5 graphically. So thinking about what we said before, 2 variables means I've got 2 dimensions that I need to represent. So I'm going to draw my xy axes again. But before I can graph it, I want to rewrite my equation into that y equals form. And so y equals -1/2 x plus 5/2. I'm going to zoom in here. I'm actually going to go up on my y-axis by a half. So just labeling that 1, 2, and 3. And I'm also going to go up by a half, scale my x-axis that way. So I know that 5 divided by 2 is 2.5. And then just let me double check. So a -1/2. So you could think of this as 2 ways. You can go down a half every one run, or you could go down 1 and then run 2. Both mean the same thing, just 2 different applications of that slope. My last point's a little weird there, but I'm going to go ahead and connect my points as best I can. And there we go. Make sure you got arrows on both ends. And our last one, how can you represent the solutions x plus 2y plus z equals 5? What would the solutions look like? Write down any ideas that you have. So to graph solutions to equations with 3 variables, you need to use a 3-dimensional coordinate system. There are many ways to do this, and I'm going to show you a few examples here. So even though they look very different, they all incorporate the x-axis, the y-axis, and the z-axis. So I'm actually just going to go through and highlight all of my x-axes in red so that we can identify where that is. And now, since this is a 3D object, I can rotate it around. So that's why my x-axis in this one doesn't seem to be in the same spot, or it's not parallel with the x-axis in the other ones. But they're still representing that same 3D space. And then I'm going to go through and do the same thing with my y-axis in blue, just so that we can visually understand where each of these pieces are happening. And then I'm going to do the same thing with the z-axis in yellow. So let's take a look at this top right one a little bit closer. You see that you have this X line that's labeled, but it's not my x-axis. However, it is parallel to my x-axis, so that's representing just that x-axis movement. Same thing with the y-axis. That parallel line, all of these blue lines are representing that y movement, and then z is going to be that straight up and down. And so now let's do our own little rough draft example. We're going to draw a little corner here. X will always be the lower left, Y will always be the lower right, and Z will always be up and down. And so let's say we have a point 2, 3, 4. And hopefully we can discern that the 2 would be the X, the 3 would be the Y, which means the 4 has to be the Z. So I'm going to scale my axes just so I have some spots to graph a little bit clearer. And then with my X value of 2, so I'm moving right along that X-axis. And I'm going to draw my line, but it's actually just the path. So I'm drawing the path of what's happening. And then same thing with my Y. So now from that X point, I am moving parallel to the Y-axis. And you can kind of see those 3 marks, how it still lines up with that Y-axis, even though I'm not on it. And then again, from that last point, from that last blue spot we landed, I'm going to take my Z straight up for 4. And this is a little harder to do when we've just done a sketch of the graph. It'll be easier on Friday when we have 3D graph paper. Now, I'm going to go through with another color. We'll do green. So these lines that we've done just represent the path, right? Our point is the only thing that matters. So all of these green lines that I'm highlighting, those are not part of my answer, right? They're just helping guide to my point. So three-dimensional, obviously we could write it as 3D. We're using X, Y, and Z. And again, we've got those 3 axes, where our X is the lower left, Y is the lower right, and Z is the up and down. And then that intersection point is our origin, just like it was in just X and Y. Same thing, X, Y, and Z, 0, 0, 0. Now I'm going to add in some dotted lines here, which you may remember from some of the other examples. These just represent the negative parts of each axis. All right. Copy the table below into your notes. Choose points in each of the locations listed at the top of the table and write in the coordinates. So I'm just drawing myself a little table at the top there for a graph at the top for a visual. So starting, points on the x-axis. So I want it to land on that lower left line where my x-axis is. And again, my points are always x, y, z. So if it's on the x-axis, let's say 1, that means I haven't moved y's, I haven't moved z's, so those are both 0. Same thing with a 7. Now I can also go negative with my x's. And if I look back up at my graph, that's where that dotted line comes in. That shows the negative directionality of an x value in a 3D graph. And you come up with the last point. Now for y, that means I haven't moved on the x, I haven't moved on the z, so those are both 0, and now I just am going to pick a number for y. And I'm going to pick another number, 10. And similarly, if I have a negative number for the y, and looking back up at the graph, my dotted blue line represents the negative y direction. And you can think of one more, and we're going to do the same thing for z. I haven't moved on the x or y, those are both 0. Could be a small number, could be a big number, and it could also be a negative number. And on the graph, that's going to be my yellow dotted line straight down, and again, that is the negative z direction. And then my last column, so I want a point that is not at all on any of my axes. So I'm just going to pick some random numbers for all 3. And you can go ahead and choose 3 more. What do we notice about the coordinates of the points? So we kind of already talked about this, but it's always nice to put it into words. So what do I notice about all of the x-axis points? If a point is on the x-axis, then y and z are going to have a value of 0, right? We haven't moved y or z. And making a conjecture just in general. So we've written about the x-axis, now I want you to write it for any axis. And I'll give you the first half. Any point that lies on an axis, dot, dot, dot. All right, in your closure, explain everything you know about the relationship between these 2 equations. And also, don't forget to study for your test, which is on Thursday when I see you next.